5%. Take a moment with that number, because it quietly rearranges everything. Everything our best theory of physics describes. Every atom, every star, every planet, and every person who has ever lived adds up to only about 5% of the universe. The other 95% is made of things we can measure but cannot name. Dark matter, holding the galaxies together, and dark energy, pushing the whole cosmos apart. Our most successful theory rests on 4 fundamental forces, and yet it explains almost nothing of what actually exists. So a growing number of physicists have begun to ask a startling question. What if there is a 5th force, one we have never admitted, hidden inside that dark majority, acting the whole time right under our noses? Is this, at last, the breakthrough modern physics has been waiting for? By the end of tonight, you will know exactly what the evidence says, and exactly what it does not. Before we begin, if slow walks around the largest questions are how you like to fall asleep, a quiet like or subscribe would mean a great deal to me. It genuinely helps me keep making these. Now, let's begin. For more than 50 years, we have believed that we understood the machinery of reality, not the details of it, not every last equation, but the shape of the thing. We believed we knew what holds the world together, and the answer, the one printed in every textbook and taught in every physics classroom on Earth, is that everything you have ever touched or seen or been is governed by just 4 forces. 4. That is the whole list: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Every atom in your body, every beam of light that has ever entered your eye, every planet and every star and every galaxy sliding through the dark, all of it can be traced back to those 4 interactions, and nothing else. Tonight, we are going to sit with the possibility that the list is wrong. Not incomplete in some small, technical way, but wrong in a way that touches almost everything there is. And to feel why that possibility is so strange, we first have to understand just how well these 4 forces have served us. Let us start with the one you know best, even if you have never thought of it as physics. Gravity is the force that keeps your feet on the ground. It is what held you in your chair a moment ago, what pulls a dropped cup toward the floor, what keeps the moon wheeling around the Earth, and the Earth falling endlessly around the sun. On the largest scales, gravity is the sculptor of the cosmos. It gathers loose gas into stars, pulls stars into galaxies, and crushes the cores of dying suns into black holes. In the modern picture, gravity is produced by energy and momentum, not merely by mass. Because mass is simply a concentrated form of energy, anything with mass makes gravity. But even things with no mass at all, like particles of light, still carry energy and momentum, and so they too are bent by it. Gravity reaches everything, because everything carries energy. Here is the first strange thing about gravity, and we will come back to it more than once tonight. For all its reach, gravity is by far the weakest of the 4 forces. It is not a little weaker. It is weaker than electromagnetism, by a factor of about 10, followed by 35 more zeros. A number so large, it does not fit inside any ordinary intuition. You can feel this weakness directly, with something as simple as a refrigerator magnet. When that small magnet clings to the door, or lifts a paperclip off the table, it is winning a tug of war against the gravitational pull of the entire planet beneath it. A whole world, 6 trillion kilograms of it, is pulling that paperclip down, and a coin-sized piece of magnetized metal wins anyway. Hold that image. The weakest force we know rules the largest structures in existence, and the reason it dominates the cosmos is not that it is strong, but that it never cancels out and it never stops. The second force you meet every waking second is electromagnetism. If gravity is the one you feel, electromagnetism is the one you live inside. It governs electricity and magnetism, obviously, but it also governs light, radio waves, and the whole of chemistry. It is the reason you can see anything at all, because vision is your eye-catching ripples of the electromagnetic field. It is the reason your phone glows, and your heart beats, and the trees turn sunlight into sugar. And it is the reason the world feels solid. When you press your hand against a table, the atoms in your hand never actually touch the atoms in the wood. What stops your hand is the electromagnetic repulsion between the electron clouds of both surfaces, pushing back against each other across a gap far too small to see. Solidity, that most obvious fact about the physical world, is an electromagnetic illusion. Nothing ever really touches anything. It only feels that way because the pushing is so strong and so immediate. The third force is the strong nuclear force, and it lives at a scale you will never feel directly, yet it is the reason you exist. Deep inside every atom, in the tiny nucleus at its heart, sit protons and neutrons, and inside each of those sit smaller particles called quarks. The strong force is what binds those quarks together, and it is what glues the protons and neutrons into a nucleus in the first place. This is no small task, because protons are all positively charged, and like charges repel. Left to electromagnetism alone, a nucleus would blow itself apart in an instant, every proton fleeing every other proton. The strong force overpowers that repulsion and holds the nucleus together anyway. Without it, there would be no atom heavier than hydrogen anywhere in the universe. No carbon, no oxygen, no iron, no gold. No chemistry, no planets, no life. Everything more complicated than the simplest atom owes its existence to a force that operates only across distances smaller than a single nucleus. The fourth and final known force is the weak nuclear force, and it is the quiet one, the one with the dullest name and some of the most important jobs. The weak force is responsible for certain kinds of radioactive decay, the kind where one type of particle transforms into another, where a neutron can turn into a proton and change the very identity of an atom. That may sound like a laboratory curiosity, but it is woven into the fire that keeps you alive. Inside the sun, the first crucial step of nuclear fusion depends on the weak force to convert one particle into another, so that hydrogen can begin its long climb toward helium. Without the weak force, that first step would never happen. The sun would not shine. Most of the stars in the sky would never have ignited. A force almost no one has heard of is part of the reason there is sunlight on your face at all. There is one more thing you need before we go further, and it is a distinction that will matter enormously tonight. Not every force you feel is actually one of the four. Take friction, the force that lets you walk without sliding, that slows a rolling ball, that warms your hands when you rub them together. Friction feels fundamental. It is not. Friction is just electromagnetism wearing a disguise. When two surfaces slide against each other, their microscopic bumps and ridges push against one another, and that pushing is nothing but the electromagnetic repulsion of electron clouds, the same repulsion that stops your hand at the table. The magnet on your fridge is the same story. Magnetism looks like its own separate power, but it is simply another face of electromagnetism, arising from the motion and alignment of electrons inside the metal. Over and over, the forces of everyday life turn out to be collective effects, surface expressions of just one of the four fundamentals underneath. This is the picture that took us most of the 20th century to assemble, and it is genuinely magnificent. Four forces. From them, everything. The falling of an apple and the orbit of a galaxy, the light of a candle and the fire of a star, the binding of a nucleus and the decay of an atom, all of it explained by the same short list. This framework, wrapped into what physicists call the Standard Model, is arguably the most successful scientific theory ever created. It predicts some quantities to better than 1 part in a billion. It has survived every experiment thrown at it for half a century. When you learn it, there is a feeling that comes. a feeling of standing on solid ground, of finally seeing the blueprint behind the world. It is worth pausing on how few pieces this blueprint actually needs, because the economy of it is part of the wonder. The entire Standard Model is built from just 17 fundamental particles. There are 6 quarks, which combine to make protons, neutrons, and a zoo of heavier cousins. There are 6 leptons, a family that includes the familiar electron and the ghostly neutrino. There are the 4 kinds of force-carrying particles that ferry 3 of the 4 forces between everything else. And there is one final particle, the Higgs boson, discovered at CERN in 2012 after a search that lasted nearly half a century, which gives many of the others their mass. 17 particles and 4 forces. From that short inventory, in principle, everything ordinary follows. When physicists talk about the elegance of the Standard Model, this is what they mean. A handful of ingredients, combined and recombined, reproducing the entire visible world to extraordinary precision. It is the closest thing science has ever produced to a complete recipe for reality. And it is precisely that feeling, that quiet confidence, that the rest of tonight is going to take apart. Because for all its triumph, this theory that explains everything turns out to explain almost nothing. And the reason why is waiting in the next part. There is a number that once you truly absorb it, is very hard to unabsorb. Everything described by the Standard Model, everything built from those 4 forces, every star you can see, and every planet, and every atom, and every person who has ever lived, all of it together accounts for only about 5% of the universe. 5%, the most successful theory in the history of science, the one that predicts nature to a billionth, is a careful and complete account of 1/20th of what exists. The other 95% is made of things we cannot see, cannot touch, and cannot yet name. We have a theory of everything that turns out to be a theory of almost nothing, and the strangest part is that we can measure exactly how much it is missing. Let us take that 95% apart, because it is not one mystery, but 2. The first piece, about 27% of the universe, is something we call dark matter. The second piece, and the larger one, about 68%, is something we call dark energy. Those 2 names are confessions of ignorance dressed up as vocabulary. We did not name them because we understand them. We named them so that we would have something to write on the chart where the understanding should be. These proportions, the 5 and the 27 and the 68, are not guesses. They come from careful measurements of the oldest light in existence, the faint afterglow of the early universe mapped by the Planck satellite, whose analysis in 2018 pinned down the recipe of the cosmos with real precision. We know the proportions, we simply do not know what 2 of the 3 ingredients are. To feel how upside down this is, picture a chemist who has written a flawless textbook of chemistry, every reaction predicted, every element accounted for, and then imagine discovering that the textbook describes only 1 out of every 20 substances in the room, and that the other 19 are made of materials that appear nowhere in its pages. That chemist would not feel finished. That chemist would feel that the real chemistry, the bulk of it, had not even begun. That is roughly where physics stands. Our theory is not wrong about its 5%. Within that 5%, it is extraordinarily right. But the theory says nothing at all about the rest, because the rest is made of something outside it. Dark matter and dark energy are not small corrections we forgot to add. They are not a decimal place we can nudge. They are entirely new things, sitting completely outside the framework, and the framework has no room to hold them. It was not always obvious that anything was missing. For a long time, the 5% looked like the whole show, because the 5% is the part that glows. Stars shine, gas clouds catch starlight. Everything ordinary matter does, it does at least partly through electromagnetism, which means it interacts with light, which means we can see it. It was only when astronomers started weighing galaxies and clusters of galaxies by their gravity rather than by their light that the accounts stopped balancing. There was far more pull than there was glow. Something massive was out there, shaping the motion of everything visible, and yet giving off no light of its own. The first hints of this go back further than most people realize. The astronomer Fritz Zwicky noticed the missing mass in a cluster of galaxies as early as 1933. He called it, in German, the dark matter, and for about 40 years, almost no one took the problem seriously. The evidence simply was not strong enough yet to force the issue. The story of Zwicky is worth lingering on, because it shows how long a genuine crack in physics can sit ignored. He was studying the Coma cluster, a swarm of galaxies bound together by gravity, and he measured how fast the individual galaxies were moving. They were moving far too fast. By his calculation, the visible matter in the cluster came nowhere near providing enough gravitational pull to hold those racing galaxies in. By the laws of motion, the cluster should have flown apart long ago, its members scattering into the dark. Something unseen, something with many times the mass of everything that glowed, had to be holding it together. Zwicky drew the obvious conclusion that there was a great deal of dark matter present, and the community mostly shrugged. It was the 1930s. The tools were crude, the assumptions uncertain, and one strange cluster was not enough to overturn anyone's picture of the universe. The idea went quiet for a generation. What eventually forced the issue was not one cluster, but the patient, repeated weighing of whole galaxies, spiral by spiral, by astronomers who kept finding the same impossible result. And every independent method that came later, from the bending of light to the pattern in the oldest radiation in the sky, converged on the same conclusion. The invisible mass was not an artifact of one bad measurement. It was really there, and there was a great deal of it. That is the headline. That changed, and we will spend real time on how it changed. But the core of it is this. Every way we have found to weigh the universe tells the same story. There is far more matter than we can see, and there is a form of energy filling space that we cannot account for at all. The visible cosmos, the one made of atoms, is a thin, bright film floating on top of something enormous and dark. And here is where the story tonight truly begins, because a natural question arises, one that sensible physicists are now asking out loud. If 95% of the universe is made of stuff we do not understand, is it really so unreasonable to wonder whether 95% of the universe might also run on forces we do not understand? We built our entire list of 4 forces by studying the 5% that shines. What if the dark majority plays by additional rules that never once showed up in the light? There is another crack in the theory, smaller than the dark universe but just as revealing, and it involves one of the most elusive particles in nature. When physicists first wrote down the Standard Model, the mathematics said that a certain particle, called the neutrino, should have no mass whatsoever. It should be a truly weightless thing, forever racing at the speed of light, never slowing, never aging. This was not a vague expectation. It was a specific prediction baked into the structure of the theory. And then, at the very end of the 20th century, experiments proved it wrong. Neutrinos do have mass. It is a tiny mass, almost unimaginably small. But it is not zero, and zero was exactly what the theory demanded. We will return to how we know this later tonight, because the story is a beautiful one. For now, hold on to the fact itself. Our best theory made a clear, confident prediction about the real world, and the real world calmly said no. And there is a third quiet failure, one we will come back to near the end, which may be the most existential of all. According to the known physics of the early universe, the Big Bang should have produced matter and antimatter in exactly equal amounts. For every particle, an antiparticle. And matter and antimatter, when they meet, annihilate each other completely, vanishing into a flash of light. If the books had balanced, the early universe should have been a brief, brilliant burst of mutual destruction, leaving behind nothing but radiation. No galaxies, no stars, no you. Yet here you are. Somehow, matter won. A tiny excess of matter over antimatter survived the great annihilation, and everything solid in the universe is built from that leftover residue. The Standard Model, for all its precision, cannot explain why the balance tipped. It is another place where the theory runs out of answers, precisely where the most important questions begin, and some physicists suspect that a new field, or a new force, may be part of why anything exists at all. So take stock of where we already stand, only 2 steps into the night. We have a theory of extraordinary power that describes 1/20th of everything. We have a universe that is mostly dark matter and dark energy, 2 substances we can weigh and map but cannot identify. And we have at least 1 particle whose behavior our theory got flatly wrong. Any one of these on its own might be dismissed as unfinished business, a loose end to be tidied up later. Together, they start to look like something else. They suggest that the neat picture of 4 forces and a closed list is not the final word, but an early chapter. Somewhere in that missing 95%, or hidden inside the small failures of the theory, there may be more physics waiting for us. And some of that physics, a growing number of researchers now believe, might take the form of a new force. Not a 5th item added to the list for the sake of symmetry, but a genuine 5th fundamental interaction, one that could explain several of these mysteries at once. Before we can hunt for such a thing, though, we have to answer a deceptively simple question. What would a 5th force even be? What would have to be true for physicists to accept that the list of 4 had finally grown to 5? That is where we turn next. It is easy to say the words a 5th force. It is much harder to say what they would actually mean, and that difficulty is the whole reason the search is so slow and so careful. You cannot simply point at something strange and declare a new force. Physics has been fooled too many times for that. So over the years, the community has settled on a set of standards, a kind of admissions test that any candidate must pass before it is allowed to join the fundamental 4. There are broadly 3 requirements, and understanding them is understanding the rules of the hunt we are about to follow. Once you know what physicists demand, every anomaly and every hint later tonight will make sense as either a promising lead or a false alarm. The first requirement is that the force must arise from a new quantum field. To feel what that means, you have to let go of a childhood picture of particles as tiny balls flying through empty space. In our deepest current theory, that picture is simply not how the world is built. Instead, reality is made of fields, and fields fill all of space, everywhere, always. There is not really a separate little object called an electron drifting around on its own. There is an electron field spread through the entire universe, and what we call an electron particle is a ripple, a localized excitation in that field. The same is true of light. There is no independent packet of light that exists apart from the electromagnetic field. A photon is a ripple traveling across that field. Empty space, the vacuum, is not empty at all. It is filled with every fundamental field layered on top of one another, quietly humming, and everything we call a particle is a disturbance in one of them. So if nature really does contain a brand new force, our framework insists it must come from a brand new field, one that nobody has yet identified, threaded invisibly through all of space alongside the ones we already know. The second requirement follows straight from the first. If there is a new field, there should be a new particle that carries the force, a messenger. In quantum field theory, this is how every force works. When 2 particles push or pull on each other, They do it by exchanging carrier particles, and each known force has its own. Electromagnetism is carried by the photon. The strong force is carried by particles called gluons, which is a fitting name, since they glue the nucleus together. The weak force is carried by heavier messengers, called the W and Z bosons, particles so massive that finding them at the European laboratory CERN in 1983 was a landmark of 20th century science. Gravity is the strange exception here. In Einstein's theory, gravity is not a force carried by a particle at all. It is the curvature of space-time itself, the bending of the very stage on which everything else moves. If gravity is ever made to fit together with quantum mechanics, physicists expect it too would have a carrier, a hypothetical particle called the graviton, but nobody has ever detected one. For a fifth force, the expectation is clear. It should have its own carrier particle, and that hypothetical messenger already has nicknames in the research papers, names like the dark photon or the Z prime, waiting for a particle that may or may not exist. The third requirement is the hardest of all, and it is the one that kills most candidates. A genuine fifth force must produce effects that cannot be explained by the four forces we already know. That sounds obvious, but the standard hidden inside it is brutal. It is not enough to discover some baffling new phenomenon. Before anyone is allowed to say the words new force, scientists must first rule out every possible ordinary explanation. They must check whether the strange result is really just gravity, or electromagnetism, or the nuclear forces behaving in a subtle way no one anticipated. They must check whether the instrument itself is fooling them, whether a cable, or a magnet, or a stray vibration is manufacturing the signal. And, crucially, they must check whether the mistake is not in the measurement at all, but in the calculation, in the theoretical prediction they are comparing against. Only when every conventional explanation has failed, when there is truly nothing in the existing toolkit that can account for what is seen, will physicists seriously entertain a fifth fundamental force. This is why the field is littered with signals that flared up, excited everyone, and then quietly faded. The bar is set deliberately at the height of the impossible, because a real fifth force would rewrite the textbooks, and you do not rewrite the textbooks on a hunch. Now put the three requirements together and notice what kind of thing you are actually looking for. A fifth force would be a new field, filling space unseen. It would have a new carrier particle, one that has escaped every detector ever built. And it would have to leave a fingerprint that nothing in the known four forces could possibly fake. When you frame it that way, the difficulty of the search becomes almost comic. You are hunting for something that, by its very definition, has been careful enough, or weak enough, or well hidden enough to avoid a century of increasingly precise experiments. It is a little like being told there is an intruder in a house, one who has never tripped an alarm, never been caught on a camera, and never left a single footprint, and then being asked to prove that they are there. And yet the reasons to keep hunting are not paranoia. They come from the universe itself, from that enormous dark majority we met a moment ago, and from the small, stubborn failures of the theory we have already hinted. There is a reason physicists keep returning to this idea, rather than dismissing it, and it is worth stating plainly before we go on. Every force we know was once a fifth force. Electricity and magnetism were thought to be separate powers until the 1860s, when James Clerk Maxwell showed they were two faces of a single electromagnetic force, and in doing so, he unified them and predicted that light itself was a wave in that field. The weak force and electromagnetism were later joined into a single electro-weak framework. Another unification, confirmed when those heavy W and Z carriers turned up at CERN. The history of physics is, in large part, the history of discovering that forces we thought were fundamental are connected, and that new ones have been hiding where we were not yet looking. So the question is not whether it is reasonable to expect more. History says it is. The question is where the next one is hiding, and if a new force exists, the most natural place for it to conceal itself is in the part of the universe we already cannot see. So that is where we go next, into the dark, to meet the invisible majority face to face, and to ask whether a fifth force might be living there all along. Before we do, it is worth understanding one more piece of the toolkit, because it will explain why a fifth force could be so hard to catch. The range of a force, how far it reaches, is set by the mass of its carrier particle. This is one of the most elegant results in all of physics, worked out by the Japanese theorist Hideki Yukawa back in 1935. A force whose carrier has no mass at all, like the photon, reaches out to infinite distance. That is why electromagnetism and gravity can act across the entire cosmos. But a force whose carrier is heavy dies away quickly, becoming feeble beyond a certain tiny range. The weak force is the perfect example. Its carriers, the W and Z bosons, are so heavy that the force effectively vanishes at distances larger than a fraction of the width of a nucleus. So when physicists imagine a fifth force, the mass of its hypothetical carrier tells them immediately what kind of thing they are hunting. A very light carrier means a force that could stretch across galaxies, which is exactly what you would want if the fifth force were behind dark energy. A heavy carrier means a force confined to distances far smaller than an atom, which could hide almost anywhere. This single rule, carrier mass sets the range, is the reason the search has to be waged on so many different scales at once, from the width of a nucleus to the span of the observable universe. And there is one more reason the idea refuses to die. If the carrier of a fifth force interacts only very weakly with the matter we are made of, or interacts with it not at all, then the force could be enormous in its effects on the dark part of the universe while remaining completely silent in every experiment we have ever run. A dark photon, a Z-prime, a light scalar field, whatever name you give the messenger, it only has to be shy enough. It has to whisper rather than shout. And a whisper, threaded through the 95% we cannot see, is precisely the kind of thing that could steer galaxies and stretch the cosmos, while never once tripping an alarm in a laboratory built from atoms. With that in mind, let us finally go and meet the dark. Suppose someone told you that there is an entire invisible substance surrounding you right now. It is passing through your body every second. It outweighs all the visible matter in the universe by about 5 to 1. And yet you have never seen it, never felt it, and never will, at least not directly. That would sound like the opening of a ghost story. It is instead one of the most solidly established conclusions in modern astronomy, and the substance has a name. We call it dark matter, and the evidence that it exists is not one clever observation, but a whole convergence of them, each pointing to the same invisible mass from a completely different direction. The first line of evidence comes from the way galaxies spin. In the 1970s, the astronomer Vera Rubin, working with Kent Ford, made careful measurements of how fast the stars in spiral galaxies orbit their centers. What she expected to find was simple and intuitive. In our own solar system, the planets closest to the Sun move fastest, and the ones farther out move slower, because the Sun's gravity weakens with distance. A galaxy, she assumed, should behave the same way. Stars near the bright central bulge should race around quickly, and stars out at the faint edges should drift slowly, because most of the visible mass is concentrated in the middle. That is not what she found. Instead, the stars at the outer edges were moving just as fast as the ones farther in. The rotation curve, as it is called, stayed stubbornly flat all the way out. By the visible matter alone, those outer stars were moving so fast they should have been flung off into space long ago. The galaxy should not have been able to hold on to them, and yet it did. There was only one way to make sense of it. There had to be far more mass in each galaxy than the light revealed, and that extra mass had to extend well beyond the visible disk, wrapping the whole galaxy in an enormous invisible halo. The stars at the edge were moving fast because they were feeling the gravity of an enormous reservoir of unseen matter surrounding them. Rubin found this same pattern in galaxy after galaxy. It was not a fluke of one system. It was a universal feature. Everywhere she looked, galaxies were embedded in halos of something that had mass but gave off no light. Her work, more than anyone's, turned dark matter from a fringe curiosity into a problem that physics could no longer ignore. The second line of evidence comes from gravity's effect on light itself. Einstein taught us that mass bends space-time, and that light traveling through curved space-time follows a bent path. This means a large enough concentration of mass acts like a lens, distorting and magnifying the light of more distant galaxies behind it. When astronomers map these gravitational lenses, they can weigh the foreground mass by how strongly it bends the light. And over, the mass they measure by lensing is far greater than the mass they see shining. Light is being bent around structures that emit no light of their own. We are, in effect, seeing the shadow of the invisible, traced out in the warped images of the galaxies beyond it. The most dramatic single piece of evidence is a cosmic collision called the bullet cluster, where two enormous clusters of galaxies smashed through one another. When they collided, the ordinary matter, the hot gas that makes up most of the visible mass, crashed together in the middle and slowed down, piling up in the center of the wreck, glowing in X-rays. But when astronomers mapped where the gravity actually was, using the lensing trick, they found it was not in the middle at all. The bulk of the mass had sailed straight through the collision and ended up on the two far sides, as if it barely noticed the crash. That is exactly what you would expect if most of the matter is a dark substance that does not interact the way ordinary gas does. The ordinary matter got stuck. The dark matter passed through almost untouched, ghost through ghost. The bullet cluster is often called the closest thing we have to a photograph of dark matter, caught in the act of separating from the ordinary stuff during a cosmic wreck. There is a fourth line of evidence, and in some ways it is the most decisive of all, because it comes from the universe at its very beginning. Scattered across the whole sky is a faint glow of microwave radiation, the leftover heat of the Big Bang, released when the universe was only about 380,000 years old and cooled enough to become transparent. This cosmic microwave background is the oldest light there is, and it is not perfectly smooth. It carries a pattern of tiny temperature ripples, hotter and colder patches, laid down by sound waves that echoed through the infant universe. The exact sizes and spacings of those ripples depend, with great sensitivity, on how much ordinary matter and how much dark matter were present at the time. When the Planck satellite measured that pattern to extraordinary precision, and the cosmologists worked backward, the answer was unambiguous. The early universe already contained about 5 times as much dark matter as ordinary matter, the very same ratio we see holding galaxies together today. This is why physicists trust the dark matter conclusion so completely. It is not one measurement. It is the spin of galaxies, the bending of light, the wreckage of colliding clusters, and the oldest radiation in existence, 4 independent witnesses, all testifying to the same invisible mass. There is even a hint, still debated, that dark matter may not be perfectly ghostly among its own kind. In some galaxy clusters, the dark matter appears to lag slightly behind or spread more smoothly than the simplest models predict, and certain small galaxies have gentler, flatter cores of dark matter than expected. One explanation on the table is that dark matter particles do gently push on each other, that they are what physicists call self-interacting, and a self-interacting dark matter is, almost by definition, dark matter that feels a force we do not know. These hints are not settled, but they are exactly the kind of subtle discrepancy that could be the first fingerprint of a hidden interaction, a fifth force acting quietly within the dark. Now here is the truly strange part, the part that pulls us toward the fifth force. For all its gravitational presence, dark matter does not seem to interact with light at all. It does not absorb light. It does not reflect it. It does not emit it. That is why it has stayed completely invisible across every telescope we have ever pointed at the sky. Whatever dark matter is, it is deaf and mute to electromagnetism, the very force that lets ordinary matter shine and be seen. And this raises a question that is easy to ask and very hard to answer. If dark matter ignores our electromagnetism, might it have interactions of its own that we cannot feel? Might dark matter particles push and pull on one another through a force that ordinary matter is simply blind to? It is worth admitting how little we can say about what dark matter actually is. For decades, the favored candidate was a heavy, sluggish particle nicknamed the WIMP, a weakly interacting massive particle, which would feel gravity and the weak force, but nothing else. Enormous, exquisitely sensitive detectors were built deep underground to catch the rare nudge of a WIMP bumping into an ordinary atom. Decade after decade, those detectors have found nothing, pushing the possible properties of the WIMP into ever tighter corners. Another leading idea is the axion, an extraordinarily light particle that would also solve a separate puzzle in the physics of the strong force. There are many other candidates besides. The point is not which one is right. The point is that after half a century of searching, we still cannot say what most of the matter in the universe is made of, and every failed search quietly strengthens the case that dark matter may be something more exotic than a single simple particle, perhaps something that answers to forces of its own. Picture what that would mean. To us, such a force would be invisible, undetectable, because we are made of the wrong stuff to feel it. But within the dark matter itself, that force might play exactly the role electromagnetism plays for us. It might let dark particles attract and repel, gather and structure, in ways we can never directly witness. And if dark matter carries even one interaction beyond the four we know, then the standard model is not just missing a particle. It is missing a whole piece of physics, an entire set of rules that governs most of the matter in existence. The fifth force, if it is real, may not act on us at all. It may act on them, on the invisible majority, and reveal itself to us only through the faintest of gravitational fingerprints. To feel how close and how strange this invisible substance really is, let us stop the argument for a moment and simply pay attention to it. Right now, without a whisper, a river of dark matter is streaming through the room you are in. It is pouring through the walls as if the walls were not there, through the ceiling, through the floor, and through you. Billions of these invisible particles are passing through your body every second, threading between the atoms, slipping through the gaps in your cells, moving through the solid bone of your chest as easily as light moves through glass. Hold up your hand in front of you. The dark tide is flowing through it right now, through the spaces between the nuclei, and not one of those particles touches a single atom of you in any way you could ever feel. There is no warmth, no pressure, no sensation of any kind. This substance outweighs everything you can see by 5 to 1, and it has been flowing through this same volume of space since before the Earth formed, since before the sun ignited, a silent, invisible current that was here long before you and will be here long after. You are standing in a downpour of the unknown, and you cannot feel a drop of it. That is dark matter, and it may be only the doorway into something larger. To make sense of what that larger thing might be, I want you to imagine a civilization that has lived its entire history underwater. They are intelligent, curious creatures, and over long ages, they have built a complete and correct physics of their world. They understand currents and tides. They understand how pressure grows with depth. They understand waves and how sound travels through water, and how the light from above fades into darkness below. Their science is not wrong. Within their world, it is flawless, predicting everything they can observe. But there is one thing their physics has no room for, because they have never encountered it. They have no concept of air. They do not know that just above the surface they have never crossed lies an entire second medium, a whole ocean of a different kind, invisible to them, surrounding their world on every side. Now imagine that one day something breaks the surface, and for the first time one of these creatures feels the air. Not water, something new, something that was always there, pressing against the boundary of their world the entire time, and yet completely absent from every equation they had ever written. That is the shock physicists are preparing themselves for. It is the possibility that our universe contains not just a few extra particles we have missed, but an entire hidden world running alongside our own, with its own forces, its own structure, and its own kind of matter, present the whole time, and invisible, simply because we are made of the wrong stuff to notice it. Physicists have a name for this idea. They call it the dark sector. The dark sector is the proposal that dark matter is not a single lonely type of particle, but potentially a rich and complicated family. Just as our visible world is not made of one particle, but of electrons and quarks and photons and all the rest, the dark world might have its own cast of characters. There could be dark electrons. There could be dark photons, carrying a dark version of electromagnetism among the dark particles. There could even be dark atoms, dark chemistry, and in the most speculative versions, dark stars, dark structures, a shadow cosmos, woven invisibly through the one we know. And the reason we would never have noticed any of it is simple. This dark world barely interacts with ordinary matter at all. The only connection guaranteed by the evidence is gravity, which is why we can weigh the dark matter and map it but never see it. Beyond gravity, there might be only the faintest of bridges, a tiny leakage of influence between our world and theirs. That faint bridge has a name too. Physicists call it kinetic mixing, and it is one of the most tantalizing ideas in the search for a fifth force. The proposal is that our photon, the carrier of ordinary light, and a hypothetical dark photon, the carrier of a dark electromagnetism, could be very slightly blended together by the rules of quantum mechanics. If that blending exists, even at an extraordinarily tiny level, then a whisper of the dark force could leak into our world, and a whisper of our force could leak into theirs. It would be like two soundproofed rooms that share a single hairline crack in the wall. Almost nothing passes through, but not quite nothing. And that almost nothing is exactly what a whole generation of experiments is now trying to detect, building instruments sensitive enough to catch the faintest possible signal of a dark photon crossing over into our side of reality. Consider how seriously physicists take this by looking at what they are actually building. Around the world, experiments are hunting specifically for dark photons and other light dark sector messengers. Some fire intense beams of electrons or protons into a target and look for the faint, rare tracks that a dark photon would leave as it decays back into ordinary particles. Some search the data from existing collider experiments for the ghost of a particle that interacts too weakly to have been noticed before. Others use precision measurements of known particles, watching for the tiny nudge a dark force would give them. The strength of the bridge between our world and the dark one is captured in a single small number, usually written as the Greek letter epsilon, the mixing parameter. If epsilon is large, the dark photon should already have shown up. Since it has not, physicists know the bridge, if it exists, must be extraordinarily narrow, and they keep pushing their instruments to detect ever fainter crossings. Each experiment that finds nothing does not close the case. It simply tells us that the crack in the wall is even thinner than we thought, and the search moves to the next level of sensitivity. There is a beautiful, almost unsettling possibility buried in these models, worth naming before we move on. If the dark sector really does have its own electromagnetism and its own light particles, then some fraction of dark matter could form dark atoms, bound together by dark forces, and cool and collapse the way ordinary gas does. That opens the door, in principle, to dark chemistry, dark structures, perhaps even dark stars, an entire shadow biology of matter running on rules we have never seen. Most of the dark matter is probably simpler than that, but the fact that physics cannot rule such things out, that the mathematics permits a hidden cosmos this rich, tells you how little we truly know about the majority of what exists. Think about what a discovery like that would mean. It would not merely add one more particle to the list. It would mean that everything we have ever studied, all of chemistry, all of biology, all of astronomy, the entire glowing 5%, is one room in a house with many rooms, and that we have spent our whole existence assuming our room was the whole building. The dark sector would be a second architecture of reality, laid over the first, obeying its own laws, and a fifth force could be the very first thread of it we manage to grasp. This is not idle speculation dreamed up to sound profound. It is a serious research program, pursued at real facilities, precisely because it fits the evidence so naturally. We know there is a great deal of matter we cannot see. We know it ignores our light. The simplest explanation for a substance that ignores our forces is that it answers to forces of its own. And here is what makes the dark sector so maddening to hunt, and so perfectly suited to hide a fifth force. If a force acts only, or even mostly, on dark sector particles, then almost every experiment we have ever performed would completely miss it. Think about how we search for new physics. We smash together particles of ordinary matter. We build detectors out of ordinary matter. We shine ordinary light and catch ordinary light coming back. Every tool we have is fashioned from the visible 5%. A force that speaks only to the dark would be silent in all of it. It could be shaping the largest structures in the universe, steering the dark halos that cradle every galaxy, and still never register in a single detector built from atoms. It would not be hiding because it is rare or far away. It would be hiding because it does not speak our language. This is why, when physicists ask themselves where a fifth force could most plausibly be hiding, the dark sector is very often the first answer. It is not a desperate guess. It is the place the logic keeps pointing to. We already have direct, fourfold evidence that most of the matter in the universe is something we cannot see. We already know that this something ignores our light and answers, so far as we can tell, only to gravity. A new force that spoke to the dark and stayed silent to us would explain, in one stroke, both why we have never detected it and why the dark matter behaves the way it does. The very invisibility that makes the fifth force so frustrating to find is also the strongest argument that it could be real, because the universe has already shown us that it is perfectly capable of hiding the majority of itself in plain sight. That is the deep strangeness we have to sit with. A fifth force, if it lives in the dark sector, could be everywhere and invisible at the same time. It could be here, in this room, threaded through the dark matter, pouring through your body this very second, acting the whole time on a kind of matter you can never touch. Reality would then be not only stranger than you imagined, but layered in a way intuition is not built to grasp, full of things that are present and undetectable at once. We have followed the dark down one path, into the matter that holds galaxies together. But the larger share of the darkness, the 68% we have barely mentioned, is stranger still. It is not matter at all. It is something pushing the entire universe apart, faster and faster, and it may be the clearest sign yet that a new force is at work. That is where we go next. Dark matter is only the smaller half of the darkness. It makes up about 27% of the universe, and for all its mystery, it at least behaves like matter. It has mass. It clumps. it gathers galaxies and holds them. But the larger share of the cosmos, about 68%, is something far stranger, something that is not matter at all. It does not clump. It does not gather. It does the opposite. It pushes. And the story of how we found it is one of the great surprises in the history of science, a moment when astronomers went looking for one thing and stumbled into a mystery that has unsettled physics ever since. The story begins in the 1990s with a simple and reasonable expectation. The universe has been expanding since the Big Bang, every galaxy drifting away from every other, the whole of space stretching outward. Everyone assumed that this expansion must be slowing down. After all, the universe is full of matter, and matter has gravity, and gravity pulls things together. So the mutual gravity of everything in the cosmos should be gently applying the brakes to the expansion, slowing it year by year, exactly as a ball thrown upward slows as Earth's gravity pulls it back. The only real question, astronomers thought, was how much it was slowing. Was there enough matter to eventually halt the expansion and pull everything back into a great collapse? Or would the universe coast outward forever, slowing but never quite stopping? To find out, two independent teams of astronomers set out to measure the deceleration directly. They did it by studying a particular kind of exploding star called a Type 1a supernova. These explosions are astonishingly useful because they all detonate at very nearly the same intrinsic brightness. They are what astronomers call standard candles. If you know how bright something truly is, and you measure how bright it appears, you can work out exactly how far away it is, the same way you could judge the distance of a candle flame in the dark if you knew the strength of every candle. By finding these supernovae in distant galaxies, the teams could measure both how far away those galaxies were and, from the stretching of their light, how fast the universe had been expanding when that light set out. Put those together across many supernovae at many distances, and you can reconstruct the history of the expansion itself. To picture just how audacious this measurement is, consider what a Type 1 supernova actually is. It happens when a dense stellar ember, called a white dwarf, the collapsed core of a dead star, pulls in matter from a companion until it crosses a critical mass, a threshold of about 1.1/5 times the mass of our Sun, at which point it detonates in a thermonuclear explosion that for a few weeks can outshine an entire galaxy of billions of stars. Because the trigger is always the same critical mass, the explosions are all nearly identical in brightness, which is what makes them such reliable standard candles. The teams were measuring the faint light of these titanic explosions that had occurred billions of years ago, in galaxies so distant the light had been traveling since before the Earth existed, and comparing their apparent brightness to work out both distance and cosmic expansion. It is a measurement of the history of the entire universe, read in the dimming glow of dying stars. In 1998, the two teams, the High Z Supernova Search Team and the Supernova Cosmology Project, led by researchers including Adam Rees, Brian Schmidt, and Saul Perlmutter, arrived at the same impossible answer. The expansion of the universe is not slowing down. It is speeding up. The distant supernovae were fainter and therefore farther away than they should have been if the cosmos had been decelerating. Instead of gravity applying the brakes, something was pressing the accelerator. Space was not merely expanding, it was expanding faster and faster, galaxies flying apart at an ever-increasing rate, as if a great outward pressure were built into the fabric of reality itself. The result was so surprising that both teams spent months trying to find the error in their own work. There was no error. The universe really is accelerating, and the discovery earned the 2011 Nobel Prize in Physics. There is a second puzzle lurking behind the acceleration, one that deepens the unease. For most of cosmic history, matter dominated the universe. Its gravity, outweighing the outward push of dark energy, and the expansion did in fact slow down. Only relatively recently, in cosmic terms a few billion years ago, did dark energy grow to outweigh matter and flip the expansion into acceleration. And here is the strange coincidence. Out of the entire 14 billion year sweep of cosmic history, we happen to be living right around the moment when matter and dark energy are comparable, when the handover is taking place. If dark energy really is a fixed constant, there is no reason it should have arranged to overtake matter just now, just as conscious beings appeared to notice it. Physicists call this the coincidence problem, and while it may be nothing more than chance, it is exactly the kind of unexplained tuning that makes some researchers suspect dark energy is not a static number at all, but something dynamic, something that evolves alongside the universe rather than sitting fixed and indifferent within it. The cause of that acceleration is what we now call dark energy, and the honest truth is that the name is all we have. We do not know what it is. We can measure what it does with real precision, and what it does is push the universe apart, but its nature is a near-total mystery. There is a leading candidate, the simplest possible explanation, and it goes back to an idea Einstein himself introduced and later regretted. The proposal is that empty space is not truly empty. Even a perfect vacuum, with every particle removed, might contain a small, fixed amount of energy of its own, an energy that belongs to space itself. This vacuum energy, often called the cosmological constant, and written with the Greek letter lambda, would act as a kind of built-in outward pressure, and because it belongs to space, the more space there is, the more of it there is. As the universe expands and space grows, the total push grows with it, which is exactly why the acceleration speeds up over time. Let yourself feel what this actually describes, because familiarity dulls how bizarre it is. Imagine watching a single distant galaxy for 1 billion years. You expect it to slow as it recedes, gravity gently reeling it back toward the rest of the cosmos. Instead, you watch it pull away faster and faster, its light stretching toward the red as the space between you and it lengthens. There is no wind pushing it, no engine, no visible cause. The emptiness itself, the vacuum between the galaxies, is somehow driving them apart. You feel the distance growing, kilometer upon kilometer of new space appearing out of nothing in the gap, a pressure with no source you can point to, so weak here in the room around you that it does nothing at all, and so relentless across the void that it is quietly rewriting the shape and the fate of everything that exists. That is dark energy. It is the dominant feature of our universe, the thing that will ultimately decide how the cosmos ends, and we cannot say what it is made of. It is worth pausing on just how much power this faint pressure holds over the future, because dark energy is not only the largest thing in the universe, it is the thing that will decide how the universe ends. If dark energy is a true constant, the acceleration will continue indefinitely, and over the coming tens of billions of years, the galaxies beyond our own local group will be carried away faster than their light can reach us, one by one, slipping over a cosmic horizon until the sky empties out. Far in the future, an astronomer in our galaxy would look up and see only a handful of nearby stars, with no evidence left that a wider universe of galaxies had ever existed. The acceleration is, in a real sense, erasing the cosmos from view, slowly, patiently, over timescales that dwarf the current age of the universe. That is the reach of a force so weak you cannot measure it in a room. And if dark energy is not constant, if it is instead a field that can grow stronger over time, the ending could be far more violent. In some models, a strengthening dark energy would eventually tear apart not just clusters and galaxies, but solar systems, planets, and finally atoms themselves, in a scenario physicists have named, with grim vividness, the Big Rip. Whether the universe drifts into a cold, dark, empty forever, or ends by ripping itself to shreds, depends entirely on the true nature of this thing we cannot yet identify. The stakes of the dark energy question are, quite literally, the fate of everything. And that is exactly why the possibility that it might be a changing field, rather than a fixed number, matters so enormously. Here is where dark energy circles back to our central question. The cosmological constant, the idea that this is just a fixed property of empty space, is the simplest explanation, but it is not the only one, and it carries a terrible problem. When physicists try to calculate how much energy empty space should contain, using the quantum theory that governs the vacuum, they get a number that is wrong, not a little wrong. It overshoots the measured value of dark energy by an amount so enormous, up to 120 orders of magnitude, that it has been called the worst prediction in the history of physics. The theory that should tell us what the vacuum energy is gives an answer larger than reality by a factor with more than 100 zeros. Something is badly misunderstood, and so some physicists have begun to wonder whether dark energy is not a fixed constant at all, but something more alive, more dynamic. Whether it might be, in fact, a new field filling the universe, and if it is a field, whether it might exert a force. That possibility, and the stunning new evidence that arrived in 2025, is where we turn now. If dark energy is not a fixed property of empty space, then what could it be? The most intriguing alternative is that it is a field, a real physical field, spread through all of space, much like the electromagnetic field, or the fields that carry the known forces, but of an entirely new kind. Physicists have given this hypothetical field a name. They call it quintessence, an old word meaning a fifth element, and the choice of name is not an accident. If dark energy is a field, then it can change. Its strength can vary from place to place, and, crucially, from time to time. It could have been stronger in the distant past and weaker now, or the reverse. And a field that fills space and influences how things move is very close to the definition of a force. Quintessence, if it is real, would be a fifth force in almost everything but name, acting not on the small scale of atoms, but on the largest scale there is, the scale of the entire cosmos. Imagine a force so unimaginably weak that you could never detect it in any ordinary setting. Not in your house, not on Earth, not even within the whole of our solar system, where the pull of the sun and planets would utterly drown it out. On every human scale, it would be nothing, undetectable, effectively zero. But across billions of light years of nearly empty space, with nothing else to compete against, that faint and patient pressure could gradually overwhelm even gravity and drive the expansion of the entire universe. This is what makes a cosmic fifth force so slippery. Its natural home is the emptiness between the galaxies, the one place we cannot build a laboratory. It would show its hand only on scales so large that the only instrument capable of detecting it is the universe itself, watched carefully over cosmic time. And in the last 2 years, we have finally built a machine to watch it that carefully. To measure the expansion history this precisely, DESI relies on a beautiful trick, a kind of cosmic ruler frozen into the structure of the universe. In the hot, early cosmos, before the first atoms formed, pressure waves rippled through the mixture of matter and radiation, spreading outward like the sound waves from a struck bell. When the universe cooled and became transparent, those waves froze in place, leaving a characteristic scale, a preferred distance, imprinted on the distribution of matter. Galaxies are very slightly more likely to be found separated by that particular distance, roughly a fixed span, than by any other. Because we know the true size of that frozen ruler from the physics of the early universe, we can compare it to how large it appears at different distances and read off exactly how much the universe had expanded at each epoch. This pattern is called the baryon-acoustic oscillations, and it is one of the most reliable measurements in all of cosmology. DESI's power is that it measures this cosmic ruler at an unprecedented number of distances, across an unprecedented volume of space. That machine is called DESI, the Dark Energy Spectroscopic Instrument, and it is doing something no one has ever done at this scale. Mounted on a telescope in Arizona, it measures the precise distances to millions upon millions of galaxies, building the largest three-dimensional map of the universe ever attempted. A map that stretches across billions of years of cosmic history. With a map like that, astronomers can do something remarkable. They can measure not just how fast the universe is expanding now, but how the expansion rate has changed over time, reading the history of dark energy the way you might read tree rings. If dark energy is a true cosmological constant, a fixed property of space, then its strength should have been exactly the same throughout all of cosmic history, unchanging from the deep past to today. But if dark energy is a dynamic field, a quintessence, then its strength should have drifted over time, and that drift would leave a subtle fingerprint in the map. In 2025, DESI released the analysis of its second great batch of data, and the fingerprint was there, faintly, tentatively, but there. When the DESI map is combined with the oldest light of the cosmic microwave background, and with the standard candles of distant supernovae, the best fit to all the data is not a perfectly fixed cosmological constant. It is a dark energy that appears to be evolving, that seems to have been slightly stronger in the past, and to be weakening now. The numbers themselves are technical. A present-day value physicists write as W0, measured at around -0.82, and a rate of change written as WA, measured at around -0.76, but the meaning is what matters. The data are whispering that the cosmological constant may not be constant after all, and if that whisper becomes a clear voice, it would mean dark energy is a living, changing field, which is very nearly the same as saying there is a fifth force acting across the whole universe. Now, I have to be careful and honest here, because this is exactly the kind of moment where excitement can outrun evidence, and this channel does not do that. The DESI result is a hint, not a discovery. The statistical strength of the signal that dark energy is evolving sits somewhere around 2.8 to 4.2 standard deviations, depending on which set of supernovae is folded in. Remember what we said earlier about the standards physicists demand. 3 standard deviations is roughly a 1 in 740 chance of being a fluke, which sounds impressive, but is nowhere near enough. The gold standard for a genuine discovery is 5 standard deviations, about 1 in 3.5 million, and the DESI hint has not reached it. There is also a real possibility that part of the apparent effect is not coming from dark energy at all, but from subtle, hard-to-model differences in the distant supernovae used to anchor the measurement. In other words, the crack might be in the data rather than in nature. We have seen that story before, and we are about to see it again in an even sharper form. There is a competing way to read all of this, and honesty requires putting it on the table. Perhaps the answer is not a new field or a fifth force at all, but a change to gravity itself. Instead of adding quintessence, some physicists have tried to modify Einstein's equations on cosmic scales so that gravity behaves a little differently across billions of light-years and produces the acceleration without any new energy. These modified gravity theories are serious work, not fringe ideas, but they took a heavy blow in 2017. That year, astronomers detected the collision of 2 neutron stars, both in gravitational waves, the ripples in space-time, and in ordinary light. The 2 signals arrived at Earth within about 2 seconds of each other, after traveling for over 100 million years, which means gravity and light travel at the same speed to 15 decimal places. Many of the modified gravity models that could mimic dark energy had predicted a difference, and in a single night, that measurement ruled a whole class of them out. It was a stark reminder that at this frontier, a beautiful theory can be killed by one clean observation, and that the surviving explanations increasingly point back toward new fields and new forces rather than tweaks to the old laws. But here is why the DESI hint still matters enormously, even in its unfinished state. For 25 years, dark energy has sat in our equations as a single silent number, the cosmological constant, a placeholder we could measure but never explain. The DESI result is the first serious, data-driven suggestion that this number might not be a number at all, but a process, something that changes, something dynamic and alive. And the significance has been growing, not shrinking, as more data comes in. The first DESI data release already leaned in this direction, and the second leaned further. If the trend continues, and if it crosses that 5 sigma threshold in the years ahead, it would be one of the most important discoveries in the history of cosmology, because it would force physics to introduce a new dynamical field into the fabric of reality, a field acting on the largest scales imaginable, a fifth force in all but name. We are not there, but for the first time, the door is genuinely open, and the universe itself is the thing rattling the handle. Before we follow that door any further, though, we have gathered a great deal, and it is worth stopping to lay the pieces out side by side. We have covered a great deal of ground, and before we go further into the cracks, I want to stop and lay the pieces out where we can see them all at once. This is the halfway point of our exploration, and it is a good moment to catch our breath, because the second half is where the story sharpens, and it will help to have the map firmly in mind before we walk deeper into it. So let us step back, slowly, and restack everything we have gathered so far. We began on solid ground, with the 4 forces: gravity, electromagnetism, the strong force, the weak force. From those 4, and a short list of particles, the standard model builds the entire visible world, and it does so with a precision that is one of the crowning achievements of the human mind. That was our starting confidence, the feeling of standing on bedrock. And then the bedrock turned out to be a thin crust, because everything that magnificent theory describes, every atom and star and living thing, adds up to only about 5% of the universe. 5%. Hold that number, because it has quietly become the emotional center of this whole story. Everything we have ever known is the small, lit corner of a house whose other rooms are dark. The first dark room is dark matter, about 27% of the cosmos. We do not see it, but we cannot miss it. It is written in the spin of galaxies, whose outer stars move far too fast for the visible matter to hold. It is written in the bending of light around invisible mass. It is written in the wreckage of the bullet cluster, where the unseen mass sailed straight through a cosmic collision. And it is written in the oldest light of all, the cosmic microwave background, which records that the early universe already held 5 times as much dark matter as ordinary matter. 4 independent witnesses, 1 invisible verdict. Something is there, it has mass, and it ignores our light completely. That deafness to light led us to a larger idea, the dark sector. If dark matter ignores our electromagnetism, perhaps it answers to forces of its own, a hidden electromagnetism, hidden particles, an entire shadow world laced invisibly through our own and connected to us by little more than gravity. And it was here that our central question first sharpened into focus, because a force that acts only on the dark would be invisible to every instrument we have ever built from ordinary matter. The very thing that makes a fifth force so hard to find, its silence in our world, is also what makes the dark sector its most natural hiding place. Then we turn to the largest darkness of all, dark energy, about 68% of the universe. In 1998, we learned that the expansion of the cosmos is not slowing, but accelerating, driven by an outward pressure built into space itself. The simplest explanation, a fixed cosmological constant, carries the worst prediction in the history of physics, wrong by more than 100 orders of magnitude, and a strange coincidence about why its handover with matter is happening just now. So some physicists propose that dark energy is not a constant at all, but a living field, a quintessence, which would be a fifth force acting on the scale of the whole universe. And then, in 2025, came the whisper. The DESI instrument, mapping millions of galaxies, found the first real hint that dark energy may be evolving after all, weakening over time rather than sitting fixed. It is only a hint, well short of the certainty physicists demand, and part of it may hide in the data rather than in nature. But it is the first time the cosmological constant has looked like it might not be constant, and if that whisper becomes a voice, it would mean a new dynamical field threaded through all of space, a fifth force, in all but name, rattling the door. It is worth being honest with ourselves about the shape of the question at this halfway mark, because we are not yet ready to answer it. We open tonight by asking whether this is the breakthrough modern physics has been waiting for, and everything we have seen so far has only deepened the question rather than resolved it. We have found the places where a fifth force could hide. We have found reasons to believe the four-force picture is incomplete, but we have not found the force. There is no detector reading, no clean signal, no moment where nature has said plainly, "Here I am." What we have is a pattern of absence, a shape cut out of our knowledge, in the outline of something we cannot yet see. And a shape is not a discovery. So we hold the question open, exactly as an honest physicist must, and carry it into the second half. There is a discipline in that patience worth naming. It would be easy, with this much circumstantial evidence, to declare that a fifth force must be real, to let the weight of the mysteries tip us into certainty. But the whole reason physics can be trusted, even when it is thrilling, is that it refuses to make that leap until the evidence forces it. Dark matter, dark energy, neutrino mass, the dark sector, the DESI whisper, these are the strongest circumstantial case that has ever existed for physics beyond the four forces. And they are still only circumstantial. Keeping both of those truths in mind at the same time, the strength of the case and the absence of proof, is the exact state of mind this second half asks of you. So that is where we stand at the midpoint. We have a theory that explains 5% of reality. We have two enormous dark unknowns that already demand new physics. We have a natural hiding place for a fifth force in the dark sector, and a tantalizing new hint that dark energy itself may be one. None of this is proof. Every piece is either a standing mystery or an unfinished measurement. But notice the shape of it. The theory is not leaking in one place. It is leaking in many places at once, and the leaks all point outward, beyond the four forces, into territory the standard model was never built to hold. Now, in the second half, we are going to look at the cracks that appear not in the sky, but in the laboratory, the small, stubborn discrepancies in our most precise experiments. Some of them have already taught us a hard lesson about how a fifth force can seem to appear and then dissolve. And one of them, the strangest of all, is a particle that broke one of the standard model's own clearest rules. A particle so faint and so elusive that catching it took some of the most extraordinary experiments ever devised. That is where we go next, to the ghost of the particle world, and the moment it proved our best theory wrong. Of all the particles in nature, none is stranger or more elusive than the neutrino. It is a particle so faint, so unwilling to interact with anything, that trillions of them are passing through your body every second, streaming out of the sun, and almost none of them touch a single atom of you. You could stack a wall of solid lead a light year thick, and a typical neutrino would sail straight through it without noticing. They are the closest thing nature has to a true ghost, matter that barely participates in the physical world at all. And it is precisely this ghost, of all things, that handed physics one of its clearest proofs that the Standard Model is incomplete. To understand why, we have to go back to what the theory originally said. When physicists first built the Standard Model, the mathematics described the neutrino as a massless particle, a thing with no mass at all, forever traveling at exactly the speed of light. This was not a casual assumption. It was woven into the structure of the theory, a specific and confident prediction. A massless neutrino would be frozen in a sense, unable to change, racing eternally without aging. For decades, this seemed perfectly consistent with everything anyone could measure. The neutrino was massless, the book said, and that was that. But there was a puzzle hiding in the sunlight. The sun produces neutrinos in enormous numbers as a byproduct of the nuclear fusion in its core, and physicists could calculate quite precisely how many should be arriving at Earth. When they built detectors to count them, they found only about a third of the expected number. 2/3 of the sun's neutrinos were simply missing. This became known as the solar neutrino problem, and for a long time, no one knew whether the fault lay in our model of the sun, our detectors, or our understanding of the neutrino itself. The answer, when it finally came, was the strangest of the three options, and it rewrote the rulebook. The neutrino comes in three types, or flavors, called electron, muon, and tau. What the experiments eventually revealed is that neutrinos can change from one flavor into another as they travel, oscillating back and forth between identities in flight. The sun's neutrinos were not disappearing. They were transforming, arriving as different flavors than the ones the early detectors were designed to catch, which is why 2/3 seemed to vanish. This phenomenon is called neutrino oscillation, and it was confirmed by two landmark experiments at the turn of the millennium. In 1998, the Super Kamiokande detector in Japan, a giant tank of ultra-pure water, watched by thousands of light sensors deep underground, found clear evidence that neutrinos produced in the atmosphere were oscillating. Then, around 2001 and 2002, the Sudbury Neutrino Observatory in Canada showed directly that the sun's missing neutrinos had changed flavor rather than disappeared. The two results together nailed it down. It is worth pausing to appreciate what those experiments actually were, because catching a ghost requires almost unreasonable ambition. Super Kamiokande is a tank holding 50,000 tons of ultra-pure water, buried a kilometer underground inside a mountain, to shield it from the constant rain of ordinary cosmic particles. Its walls are lined with tens of thousands of sensitive light detectors, watching the darkness for the faint flash that occurs on the rare occasion a neutrino does interact with the water. The Sudbury Neutrino Observatory, 2 kilometers down in a Canadian nickel mine, used 1,000 tons of heavy water, a rare and precious form of water, precisely because it could catch all three flavors of neutrino and prove that the missing solar neutrinos had merely changed their identity. These are among the most patient machines ever built, sitting in the dark for years, waiting for a particle that almost never stops, to reveal itself in a single flicker of light. That such delicate detective work could overturn a prediction of our best theory is a proof to how seriously physics takes the smallest of discrepancies. Here is the part that matters for our story. The rules of quantum mechanics are strict on this point. A particle can only oscillate between flavors if those flavors have different masses, and a particle can only have different masses if it has mass at all. So the very fact that neutrinos oscillate is an ironclad proof that they are not massless. The Standard Model had said 0. Nature said no. Neutrinos have mass, tiny but real, and the discovery was so important that it earned the 2015 Nobel Prize in Physics, awarded to Takaaki Kajita and Arthur MacDonald for leading those two experiments. For the first time, physics had a concrete, undeniable measurement of the real world directly contradicting a clear prediction of its best theory. How tiny is that mass? almost unimaginably small, and pinning it down has become one of the great precision challenges in physics. The neutrino is at least hundreds of thousands of times lighter than the electron, itself already a featherweight among particles. Measuring it directly requires watching the faint edge of a radioactive decay with extraordinary care. The leading experiment doing this is called Katrin in Germany, which studies the decay of tritium, a heavy form of hydrogen, and measures the energy of the emitted electrons with extraordinary precision. In 2025, Katrin announced the tightest direct limit yet on the neutrino's mass, showing it must be less than about 0.45 electron volts, a fantastically small quantity, and the experiment is still running, pushing toward even finer sensitivity in the years ahead. We are, quite literally, weighing a ghost, and the fact that we can measure a mass this small at all on a particle that passes through a light year of lead without stopping is one of the quiet triumphs of modern experimental physics. Now, why does a tiny neutrino mass point toward new physics, and perhaps toward a new force? Because the Standard Model does not merely fail to predict the mass, it has no natural mechanism to produce it in the ordinary way it gives mass to other particles. To explain why the neutrino has any mass at all, and why that mass is so extraordinarily small, physicists have had to reach beyond the Standard Model. The favored explanation is called the seesaw mechanism, and it works by introducing a new, very heavy partner particle, a kind of neutrino that has never been seen, whose enormous mass forces the ordinary neutrino's mass to be tiny, the way a heavy child on a seesaw lifts a light one high into the air. That heavy partner, if it exists, is entirely new physics, and in many versions of the theory, it is tied to new interactions, potentially even a new force, operating at energies far beyond anything we can currently reach. There is an even more tantalizing thread here, one that reaches all the way back to a puzzle we raised in the first half. Remember the question of why the universe is made of matter at all, when the early cosmos should have produced equal amounts of matter and antimatter that annihilated into nothing. One of the most compelling explanations physicists have for that imbalance runs directly through these heavy neutrino partners. The idea, called leptogenesis, is that the decay of those heavy neutrinos in the very early universe could have tipped the balance ever so slightly in favor of matter, leaving behind the tiny excess from which every galaxy, every star, and every atom in your body was later built. If that idea is right, then the same new physics that gives the neutrino its feather-light mass may also be the reason anything exists at all. One thread, connecting the lightest ghost in nature to the survival of the entire material universe, and pointing, once again, beyond the four forces. So the neutrino is not just a footnote, it is a working example of the exact process this whole video is about. A confident prediction of the four-force theory turned out to be wrong. The correction required reaching beyond the Standard Model, and the most natural explanations for the correction involve new particles and quite possibly new interactions, the same territory where a fifth force would live. The ghost that barely touches the world, nonetheless, left a fingerprint on our deepest theory, and the fingerprint says, plainly, there is more. But the neutrino is a crack we are confident about. The next cracks we examine are more treacherous, because they teach the hardest lesson in this entire search. The lesson of how a fifth force can seem to reveal itself, and then, on closer inspection, quietly disappear. The dark universe gives us reasons to expect a fifth force, but there is another place physicists have gone hunting for it, not out in the cosmos, but down in the laboratory, in the most precise measurements human beings have ever made. The idea is simple and powerful. If a fifth force exists, even a very feeble one, it should leave a tiny fingerprint on the behavior of ordinary particles, a minuscule deviation from what the four-force theory predicts. So physicists measure a handful of quantities with almost insane precision, calculate what the standard model says they should be, and compare. If the measurement and the prediction disagree, and if nothing known can explain the gap, that gap could be the first whisper of new physics. Two of these laboratory cracks have dominated the conversation, and together they teach the single most important lesson in this entire search. The first is one of the most famous numbers in physics, and it concerns a particle called the muon. The muon is a heavier, short-lived cousin of the electron, identical in almost every way except that it is about 200 times more massive and decays in a couple of millionths of a second. Like the electron, the muon behaves like a tiny spinning magnet, and the strength of that magnetism can be both measured and calculated with extraordinary precision. A simple early theory predicted that a certain number describing this magnetism, called the G factor, should be exactly 2. But the real value is not exactly 2, it is very slightly more, and that tiny excess, the amount by which G exceeds 2, is where the interesting physics lives. This is why the experiment is called muon G-2. That excess exists because the muon is never truly alone. In quantum theory, the empty space around it is a boiling sea of virtual particles, flickering in and out of existence, and the muon constantly interacts with them. Every kind of particle that exists contributes to this seething cloud, and each one nudges the muon's magnetism by a tiny amount. So when physicists calculate the expected value of G-2, they are, in effect, adding up the influence of every particle in the standard model. And here is the beautiful implication. If there were an unknown particle out there, a carrier of a fifth force, it too would contribute to that cloud, and it would push the measured value away from the prediction. A disagreement between measurement and theory could therefore be the shadow of a particle we have never seen. For years, there was a disagreement, and it was tantalizing. An experiment at Brookhaven National Laboratory in the early 2000s measured G-2 and found it sitting above the theoretical prediction by an amount that reached about 3.5 standard deviations, enough to make physicists lean forward. Then the experiment moved to Fermilab, near Chicago, where a bigger and more precise version took over. Its centerpiece, a giant magnetic ring that had been transported across the country in an epic journey by barge and truck. Fermilab released results in 2021 and again in 2023, each more precise, and each confirming that the muon's magnetism sat stubbornly above the prediction. And then, on the 1st of July 2025, the experiment released its final result, the most precise measurement of the muon's magnetism ever made, pinning it down to a precision of about 127 parts per billion. Compared against the theoretical consensus that had stood in 2020, the gap now exceeded 5 standard deviations, the gold standard that normally signals a discovery. It looked, for a moment, like new physics had finally arrived. But this is where the hardest lesson in the search reveals itself, and it is a lesson in humility. The measurement was rock solid. The problem lay on the other side of the comparison, in the theoretical prediction. The single hardest part of calculating the muon's magnetism is accounting for the influence of the strong force, the swirl of quarks and gluons that make the messiest contribution to the virtual cloud. There are 2 different ways to compute this piece, and they disagree with each other. One method uses data from particle collisions. The other uses a massive supercomputer technique called lattice calculation. And in 2025, as the lattice calculations improved, the theoretical prediction shifted, moving much closer to the measured value. The muon G-2 theory initiative published an updated prediction in May of 2025 that was substantially higher than the old consensus, and statistically at odds with it. In other words, the famous 5 sigma gap may not be a sign of a fifth force at all. It may have been a gap between the measurement and an outdated calculation, and as the calculation catches up, the crack appears to be closing. The disagreement between the two ways of calculating the muon's magnetism is worth dwelling on, because it is itself an unsolved puzzle hiding inside the first one. One method takes data from real particle collisions and uses it to estimate how the swirl of quarks and gluons contributes to the muon's magnetism. The other, the lattice method, simulates that swirl directly on enormous supercomputers, dividing space and time into a fine grid and grinding through the strong force equations by brute force. In principle, both should give the same answer, because both are describing the same piece of physics. They do not. They disagree with each other at a level of about 3 standard deviations, and nobody yet knows which one is right or why they differ. That means the muon story contains 2 mysteries stacked on top of each other. Is the muon telling us about a fifth force, or about an error in one of these calculations, or about some subtle problem in the collision data itself? Until the 2 methods are reconciled, the anomaly cannot be cleanly interpreted, and this is exactly why the excitement of 2021 has cooled into careful uncertainty by 2025. Sit with what that means, because it is the whole discipline of this field in a single story. Here was the most celebrated anomaly in particle physics, a 5 sigma discrepancy, exactly the kind of thing that should announce a new force. And the most likely explanation now is not new physics, but that we had not yet computed the old physics well enough. This is the third criterion we spoke of earlier, biting down hard. Before you can claim a fifth force, you must rule out that the anomaly lives in your own mathematics. The muon has not closed the door on new physics entirely. The situation is still genuinely unsettled, but it has taught a generation of physicists to hold their excitement lightly, because a crack in the theory and a crack in the calculation can look exactly alike. The second laboratory crack is stranger and less famous, and it goes by the name X17. In 2016, a group of physicists in Hungary, led by Attila Krasznahorkai, was studying the decay of an excited form of the beryllium nucleus. When such a nucleus relaxes, it can emit a pair of particles, an electron and its antimatter twin, a positron, flying apart at various angles. The theory predicts a smooth, gently falling distribution of those angles, but the Hungarian group reported a bump, an unexpected excess of pairs flying apart at an angle near 140 degrees. A bump like that is exactly what you would expect if the nucleus were occasionally producing a brand new particle, one with a mass of about 17 mega-electron volts, which then decayed into the electron-positron pair. They called the hypothetical particle X17, and some theorists proposed it could be the carrier of a fifth force, a force so shy that it had earned the nickname protophobic, meaning it seemed to avoid protons and interact mainly with neutrons, which would explain why it had never shown up elsewhere. What makes X17 so maddening is that the evidence has refused to resolve, and the years since have only muddied it further. The Hungarian group reported seeing the same bump in other nuclei too, in helium and in carbon, always pointing to a particle of roughly the same 17 mega-electron-volt mass, which its supporters call remarkable consistency and its critics call suspicious. Then, in early 2024, an independent group in Vietnam, using a different kind of detector, reported that they too saw the beryllium anomaly, which was the first real independent support. But in June of 2025, a large and careful experiment called MEG2 reported that it saw no significant excess where the anomaly should be, effectively excluding the original observation at a high level of confidence. So the score stands at 1 independent confirmation and 1 independent contradiction, with the original group still standing by its result. This is not the clean picture of a discovery. It is the messy, unresolved, deeply human reality of research at the very edge, where a signal can be real or an artifact, and where it can take a decade or more to tell the difference. So what do these two laboratory cracks tell us, taken together? They tell us to be careful, and they tell us to keep looking. The muon story warns us that even a 5 sigma anomaly can dissolve into a theoretical error. The X17 story warns us that a signal can hover for years in a limbo between confirmation and refutation. Neither of them is, right now, a confirmed fifth force. And yet neither of them is dead. Both are exactly the kind of small, stubborn discrepancy that, in the history of physics, has sometimes turned out to be nothing and has sometimes turned out to be everything, which raises the question we have been circling all night. If a fifth force is real, and if it keeps slipping through our fingers like this, then why is it so incredibly hard to catch? Why, with all our precision, does it stay hidden? That is the question we turn to now. If a fifth force exists, we have to confront an uncomfortable fact. It has managed to avoid detection through more than a century of increasingly precise experiments, through underground detectors and giant colliders and satellites in orbit. A force that could do that is either extraordinarily good at hiding, or it hides for reasons built into its very nature. And when physicists work through the possibilities, they find that a real fifth force would have not one, but several excellent ways to stay concealed, each of them a natural consequence of how forces work. Understanding these hiding places is understanding why the search has been so hard, and why the absence of a discovery so far is not the same as evidence that there is nothing to find. The first way a fifth force could hide is by being unimaginably weak. We already know that forces come in wildly different strengths. Gravity, remember, is weaker than electromagnetism by a factor with more than 30 zeros, and yet gravity rules the cosmos. If a fifth force were weaker still, weaker even than gravity, it could be threaded through everything and still be far too faint to register in any experiment we have built. Its effects on any single particle would be so minuscule as to vanish beneath the noise. A force does not have to be strong to be real, and it does not have to be strong to matter, especially if it acts coherently across enormous scales, the way dark energy would. Sheer feebleness is the simplest cloak of all. The second way a fifth force could hide is by having a very short range. We met this idea earlier in Yukawa's rule that the mass of a force's carrier sets how far the force reaches. A massless carrier gives infinite range. A heavy carrier gives a range so short that the force effectively switches off beyond a tiny distance. The weak force is confined to distances smaller than an atomic nucleus for exactly this reason. A fifth force with a heavy enough carrier could operate only across distances far smaller than anything we can easily probe, doing its work in a domain too small for our instruments to reach into. It would be like a conversation conducted in a whisper, so quiet that you would have to press your ear to the exact right spot to hear it, and we have not yet found the spot. The third way is the most elegant and the most cunning, and physicists have developed real, detailed theories of it. It is the idea that a fifth force could hide by making itself weaker precisely where we look for it. These are called screening mechanisms, and they are genuinely beautiful pieces of physics. In one version, called the chameleon mechanism, proposed by the physicists Justin Corey and Amanda Weltman, the mass of the fifth force's carrier depends on how much matter is around it. In a dense environment, like the surface of the Earth or the inside of a laboratory, the carrier becomes heavy, which, by Yukawa's rule, makes the force short-ranged and feeble, shrinking it down to nothing right where our experiments sit. But out in the near-empty voids between galaxies, where there is almost no matter, the carrier becomes light, and the force stretches out and grows strong. A chameleon force would be powerful across the cosmos and invisible in the lab, changing its behavior to match its surroundings, exactly as its name suggests. There are cousins of this idea, each achieving the same trick by different means. The symmetron mechanism has a fifth force that switches off in dense regions because a symmetry is restored there, turning the force's effect to zero wherever matter is thick. The Weinstein mechanism suppresses the force non-linearly in the neighborhood of any massive body, so that near the Sun or the Earth, the fifth force is quenched, while far from any large mass it revives. What all these mechanisms share is a kind of built-in stealth. They describe a force that could be entirely real, could be driving the acceleration of the universe, and could still pass every tabletop test we throw at it, because it is designed, by its own physics, to turn itself down wherever an experiment is dense enough to catch it. It is almost as if the force were engineered to hide exactly where we stand, present the whole time, and quietest in the one place we are looking. And of course, there is the hiding place we have already explored at length, the dark sector. A fifth force that couples only, or mostly, to dark matter would be silent to every instrument made of ordinary atoms. It would not need to be weak, and it would not need to be short-ranged, and it would not need to screen itself. It would simply be speaking a language our detectors cannot hear, acting powerfully on the invisible majority and never once touching the visible 5% from which all our experiments are built. Between feebleness, short range, screening, and dark-only coupling, a real fifth force has an abundance of ways to remain exactly what it has been so far, present in its effects on the cosmos and absent from every direct search. This kind of hunt has a longer history than most people realize, and it began with a false alarm that taught the field how to search. In 1986, the physicist Ephraim Fishbach and his collaborators reanalyzed a set of old, famous experiments on falling bodies and claimed to find evidence of a new force, one that coupled to a property of matter called baryon number and acted over a range of perhaps a few hundred meters. For a brief electric period, it looked as though a fifth force had genuinely been found, and laboratories around the world raced to test it. Within a few years, the careful follow-up experiments had ruled it out. Fishbach's specific force was not real, but the episode was not a waste. It established the entire modern template for how you look for a fifth force, the precision equivalence principle tests, the careful comparison of how different materials fall, the systematic mapping of strength against range. Almost every experiment we have described tonight is, in a sense, a descendant of that 1980s false alarm, refined across 4 decades into the exquisitely sensitive searches we run today. Now, none of this means physicists are helpless, or that the absence of a discovery tells us nothing. Quite the opposite. Every experiment that looks for a fifth force and finds nothing carves away another region where the force cannot be hiding, tightening the noose. These null results are not failures, they are information. Consider the tests of what is called the equivalence principle, the rule that all objects fall at exactly the same rate, regardless of what they are made of. A fifth force that pulled on different materials by different amounts would violate this principle, causing, say, a piece of platinum and a piece of titanium to fall at very slightly different rates. So physicists test the principle with fanatical precision. Delicate instruments called torsion balances, refined over decades by a group at the University of Washington, often nicknamed EOT-WASH, have confirmed that materials fall at the same rate to about 1 part in 10,000 billion. And a satellite mission called Microscope, whose final results were published in 2022, carried this test into the perfect free fall of orbit and confirmed the equivalence principle to about 1 part in 1,000 trillion, 100 times better still. Those extraordinarily precise null results, along with others, do real work. Tests of gravity at very short ranges, down to distances smaller than a millimeter, constrain fifth forces that might have come from extra dimensions of space. The neutrino burst from a supernova seen in 1987 put limits on how new forces could behave over cosmic distances. Collider experiments have pushed the possible mass of a heavy Z-prime carrier up above several thousand times the mass of a proton, ruling out the simplest versions. Each of these measurements draws a boundary, saying, if a fifth force exists, it cannot be here, or here, or here. The space where it could still be hiding shrinks year by year. It helps to picture all of this as an enormous map of possibilities. Along one direction of the map, you have the strength of the hypothetical force, from strong down to unimaginably feeble. Along another, you have its range, from cosmic down to smaller than a nucleus. Every conceivable fifth force sits somewhere on that map, at some particular strength and some particular range. And what a century of experiments has been doing, patiently, is shading in the regions where a force cannot be, because if it were there, we would already have seen it. The strong, long-range corner was ruled out long ago, because a force like that would be as obvious as gravity. Piece by piece, the torsion balances and the satellites and the colliders and the supernova observations have blacked out more and more of the map. What remains unshaded is the territory of the feeble, the short-ranged, the screened, and the dark-coupled, the exact hiding places we have described. The search is not wandering blindly. It is methodically cornering its quarry into the last regions where it could still be concealed. And that is precisely why the search feels, to many physicists, like it is closing in rather than coming up empty. We have not found the fifth force, but we have learned, with great precision, an enormous amount about where it is not, and the territory that remains is exactly the kind of place, feeble, screened, dark-coupled, where the deepest new physics could live. See whether that closing in is really leading somewhere. It helps to remember how every previous revolution in physics actually began. There is a temptation, when a search drags on for decades without a clean discovery, to conclude that there is nothing there. But the history of physics tells a very different story, and it is worth walking through, because it changes how you read every hint we have discussed tonight. The great revolutions in physics did not usually begin with a thunderclap, a single dazzling experiment that overturned everything at once. They began with small cracks, with tiny, stubborn discrepancies that most people were content to ignore, numbers that were just slightly off and would not go away until someone took them seriously enough to follow them all the way down. Again and again, the cracks that looked like rounding errors turned out to be doorways into entirely new physics. Consider the planet Mercury. Through the 1800s, astronomers tracked its orbit with growing precision, and they found something faintly wrong. The point of Mercury's closest approach to the Sun was slowly shifting around, drifting, and when they calculated how much of that drift Newton's gravity could account for, they came up short by a tiny amount, about 43 seconds of arc per century. 43 arc seconds. It is an almost absurdly small quantity, a sliver of an angle, the width of a coin seen from kilometers away, accumulating over 100 years. For decades, astronomers tried everything to explain it within known physics. They proposed a hidden planet closer to the Sun. They questioned their measurements. Nothing worked. And then, in 1915, Albert Einstein published his general theory of relativity, a complete reimagining of gravity as the curvature of space-time, and it predicted Mercury's extra drift exactly, with no adjustment. That tiny 43 arc-second crack had been a window onto a whole new understanding of gravity, space, and time. Consider the glow of hot objects. In the late 1800s, physicists studied the light given off by warm bodies, and their best theory made a catastrophic prediction. It said that a hot object should radiate an infinite amount of energy at short wavelengths, a nonsensical result that came to be called the ultraviolet catastrophe. The theory was not slightly off. It was infinitely off, and yet everything else about it seemed correct. Resolving that crack required a desperate and radical idea. In 1900, Max Planck proposed that energy could not be radiated in a smooth, continuous flow, but only in discrete little packets, which he called quanta. It was a mathematical trick that he himself found troubling, and it worked perfectly. That single reluctant step, taken to patch one stubborn discrepancy, was the birth of quantum mechanics, the theory that would go on to remake our entire picture of reality at the smallest scales. Consider radioactive decay. In the early 20th century, physicists studying a particular kind of decay, called beta decay, found that energy seemed to be going missing. When a nucleus decayed and spat out an electron, the electron did not carry away the fixed amount of energy that the law of energy conservation demanded. Instead, it carried a range of energies, always somewhat less than expected, as if some energy were simply vanishing. This was so troubling that a few physicists were prepared to abandon the sacred principle of energy conservation itself. But in 1930, Wolfgang Pauli proposed a desperate rescue. He suggested that an unseen particle was being emitted alongside the electron, an almost undetectable ghost that carried away the missing energy. He apologized for the idea, writing that he had done a terrible thing by proposing a particle that could never be detected. That ghost was the neutrino, and it was not detected for another 26 years, in 1956. The same neutrino, as we have seen, would later break the Standard Model's own rules. A missing sliver of energy became one of the most important particles in nature. Now, honesty demands a counterexample, because not every crack leads to a revolution, and physicists know this better than anyone. Consider the planet Uranus. In the early 1800s, astronomers found that its orbit, too, refused to match predictions. It wandered from where Newton's gravity said it should be, just as Mercury did. Here was another stubborn discrepancy, but this one had an ordinary explanation. The wobble was caused by the gravitational tug of an undiscovered planet farther out, and when astronomers pointed their telescopes to where that tug implied a planet should be, they found Neptune, right on cue, in 1846. No new physics was needed. The crack was real, but it was closed by known laws and a new object, not by a new force. This is the sober lesson that sits alongside the inspiring one. Sometimes a discrepancy is a doorway to a new universe, as Mercury was, and sometimes it is just a hint of one more ordinary thing we had not yet noticed, as Uranus was. The muon anomaly may well turn out to be a Uranus rather than a Mercury, a crack closed by better calculation rather than new physics. Part of the discipline of this search is holding both possibilities open at once. I want you to stand for a moment in the room where a revolution starts, because it never feels the way the history books make it sound. Place yourself beside an astronomer in the 1800s, bent over columns of figures describing Mercury's orbit, staring at a discrepancy of 43 arcseconds that will not close. It is tiny. It is embarrassing. Any reasonable colleague would tell you to assume a measurement error and move on, and yet something in the back of the mind refuses to let it rest. Or place yourself beside Pauli in 1930, pen in hand, about to propose a particle he is certain can never be found, feeling faintly ridiculous, apologizing even as he writes. This is what a crack in reality actually feels like from the inside. Not a blinding flash of certainty, a small wrong number that keeps you awake, a quiet insistence that the universe is trying to tell you something, if only you are stubborn enough to keep listening. Every revolution we now teach as obvious began in exactly that uncomfortable, uncertain place. So look again at the cracks we have gathered tonight, and see them in this light. Dark matter, holding galaxies together with mass we cannot see. Dark energy, pushing the cosmos apart, and the 2025 hint that it may be changing. The neutrino, carrying a mass the theory forbade. The muon, and the X-17 bump, hovering in their unresolved limbo. Each one is a small wrong number that will not go away. Any single one of them might, in the end, turn out to be noise, or a miscalculation, exactly as the muon anomaly may be dissolving now. But the pattern, the sheer number of independent places where our best theory strains and leaks, is exactly what the eve of a revolution has always looked like. History does not guarantee that a fifth force is waiting on the other side of these cracks. But history does insist that we take the cracks seriously, because this is precisely how every new layer of reality has ever announced itself. And this time, we are not merely waiting and watching. We are building instruments of a precision that would have seemed like magic to Pauli or Einstein, machines designed specifically to catch a fifth force if it is there. Physicists are constructing atom interferometers, devices that use the wave nature of atoms themselves as exquisitely sensitive rulers, capable of detecting accelerations of about 1 part in 1,000 trillion, hunting for the faintest tug of a new force or a passing wave of ultralight dark matter. They are using arrays of the most precise atomic clocks ever built to search for tiny variations that a fifth force might cause. They are comparing the properties of different isotopes of atoms with such precision that a new force coupling to neutrons would reveal itself in a subtle mismatch, a technique made possible by optical atomic clocks so stable they would not gain or lose a second over the entire age of the universe. Each of these approaches attacks the problem from a different angle, at a different scale, precisely because a fifth force could be hiding in so many different places. Some hunt the cosmos, some hunt the atom, some hunt the empty space in between, and together they are sweeping through the last unshaded regions of that map of possibilities we spoke of, closing off hiding place after hiding place. And they are planning ever larger surveys of the cosmos to turn the Deci whisper into either a clear voice or a definitive silence. The search has never been better equipped. A physicist working today can measure things that were literally unmeasurable a single generation ago, probing forces 1 trillion times fainter than the ones Fishback's contemporaries could test, and mapping the expansion of the cosmos across billions of years with a fidelity that would have seemed like fantasy in the 1990s. When a field gains that much new power to see, it very often finds something. And history suggests that this is exactly the kind of moment when the small cracks finally give way. Which brings us, at last, back to the question we started with. So, is this the breakthrough modern physics has been waiting for? We have spent this whole journey circling that question, promising an honest answer by the end, and now it is time to give one. And the honest answer, the one the evidence actually supports, is this: not yet, not a confirmed breakthrough, not a discovery you could carve into stone. As of tonight, there is no fifth force sitting in a detector, no clean signal that nature has stepped forward and revealed a new interaction. Anyone who tells you the fifth force has been found is running ahead of the evidence. That is the sober truth, and this channel will always give you the sober truth over a comfortable headline. But that is not the whole answer, and the rest of it is genuinely remarkable. Because while there is no confirmed breakthrough, the case that something lies beyond the four forces has never in history been stronger than it is right now. Look at what we have assembled. We have dark matter, established beyond reasonable doubt by 4 independent lines of evidence, making up more than a quarter of the universe and answering, so far as we can tell, to nothing in the standard model. We have dark energy, the largest component of reality, driving an acceleration we cannot explain, and now, as of 2025, showing the first real hint that it may be a dynamic, evolving field rather than a fixed constant. We have the neutrino, a particle whose mass the theory flatly forbade, forcing us to reach beyond the standard model to explain it. And we have the small laboratory cracks, the muon and the X17, which teach caution even as they keep the question alive. No single one of these is proof of a fifth force. We have been careful about that all night. The muon anomaly may be dissolving into a calculation error. The DESI hint has not reached the certainty physicists demand. The X17 bump hovers unresolved. But step back and look at the shape of the hole. Our best theory is not leaking in one place. It is leaking in many places at once, and all of the leaks point in the same direction, outward, beyond the four forces, into the enormous dark majority of the universe we cannot see. That convergence is the strongest reason to believe that the four-force picture is not the final word. And a fifth force, a new field with a new carrier, acting on the dark sector or on the scale of the cosmos, remains one of the most natural and economical ways to complete the picture. It could, in a single stroke, touch dark matter, dark energy, the neutrino's mass, and even the reason the universe is made of matter at all. Where could a fifth force actually be then? And where could it be hiding? By now you know the answer. It could be threaded through the dark matter, a force we cannot feel, because we are made of the wrong stuff. It could be the true identity of dark energy, so weak it is nothing in this room, and yet, across billions of light years, strong enough to move the entire cosmos. It could be screened, turning itself down to nothing, exactly where our experiments are dense enough to catch it. It could be sitting right under our noses, in the 95% of reality we have never been able to touch, present the whole time, and quietest in the one place we stand, hiding in plain sight, in the most literal sense physics allows. When we first used that phrase tonight, it was almost a figure of speech, a way of saying the answer might be close. Now it has become something precise and technical. A screened force really would grow silent exactly where a laboratory is dense enough to catch it. A dark-coupled force really would act everywhere and touch nothing we are made of. The universe is not merely capable of keeping a secret, it appears to be capable of keeping one in the very room you are sitting in the space between your own atoms, and giving no sign at all. And here is the thought I want to leave you with, the one that turns this from a story about physics into a story about being alive at a particular moment. Everything you have ever known, everything anyone has ever known, is that small lit 5%, the bright corner of a house whose other rooms are dark. For all of human history, we did not even know the dark rooms were there. Now we know. We can measure them, map them, weigh them, and feel, at the edges of our most precise instruments, the faint suggestion of forces we have not yet named. To live right now, at the moment when the cracks are visible, and the answer is not yet in hand, is a rare and strange privilege. We are standing at the edge of the map, in the uncomfortable, thrilling place where every revolution has begun, listening to a universe that is still keeping most of its secrets. There is a particular kind of peace in that honest answer, and I have come to think it is one of the quiet gifts of following physics closely. We are so often taught that not knowing is a failure, a gap to be embarrassed by and rushed past. But sit with it differently for a moment. To be able to say we do not know yet, and to say it not with frustration but with wonder, is a rare and human thing. It means we have measured carefully enough to know exactly where the edge of our knowledge lies. It means we have been honest enough not to fill the darkness with comfortable stories. And it means we are living in one of those uncommon moments, the moment before a discovery, when the question is sharp and open, and the answer has not yet arrived to close it. Most people who have ever lived did not even know these questions existed. We get to hold them, unfinished, in our hands. And think about how much has already changed just within a single lifetime of physics. A century ago, we did not know the universe was expanding at all. 50 years ago, Dark matter was a fringe curiosity most physicists ignored. 30 years ago, no one knew the expansion was accelerating. 25 years ago, we did not know for certain that neutrinos had mass. And only this year, in 2025, did the first real hint arrive that dark energy might be a living, changing thing. The map of our ignorance is not static. It is being redrawn, piece by piece, faster now than ever before, by instruments of a delicacy that borders on the miraculous. Whatever the fifth force turns out to be, or turns out not to be, the direction of travel is unmistakable. We are learning to see into the dark. So, is this the breakthrough modern physics has been waiting for? Not yet, but perhaps closer than it has ever been. And whether or not a fifth force is confirmed in your lifetime or mine, the search itself may be the most important thing physics is doing, because it is the search for the other 95% of everything. Somewhere inside that darkness, there is very likely another force quietly shaping reality, waiting for us to learn how to listen. And the next time you hold up your hand and feel how solid and complete the world seems, remember that it is only the thinnest bright film on top of something enormous, and that we have only just begun to see into the dark. Remember, too, where all of this began tonight. It began with small cracks. A sliver of an angle in Mercury's orbit. A missing sliver of energy in a radioactive decay. And now, in our own time, a handful of new small cracks. In the spin of galaxies. In the acceleration of the sky. In the mass of a ghostly particle. In the faint whisper of an instrument mapping the cosmos. The whole history of physics tells us that this is exactly what the ground looks like just before it shifts. Whether these particular cracks lead to a fifth force, or to something stranger still, or quietly close like the wobble of Uranus, no one can yet say. But the cracks are real, and the cracks are where the next physics lives. That is the one thing we can be sure of tonight, and it is enough to keep the search burning for a generation. Thank you for spending this time with me, drifting through the edges of what we know and do not know about the forces that hold reality together. If this kind of slow walk around the largest questions is how you like to end your day, a like or a subscribe would mean a great deal to me, and it genuinely helps me keep making these. Rest well tonight, and may you never quite look at the empty space around you the same way again.